All right, I think we're going. Here we go. So, this works better when you turn it on. Talk about functions. Remember what I talked about the other day. We are dealing only with real numbers, and we're dealing in a function system. So we talked about how that sideways parabola is not good because it's not a function. We want only functions in this class, and then we're going to do just about everything conceivable with a function. I like to start slideshows with an objective list, and some of these things you'll be able to check off right away. Some of them you might struggle with, or you might be happy that we're going to cover it today. For instance, do you understand function notation? Now, algebra 1, y equals blah, blah, blah. Calculus, f of x. And you probably made that transition earlier, but we use everything for f of x. Do you know how to do a domain and range? You may have learned, what is it, ceilings and floors, doors and windows, or something stupid like that. Can you graph a function? We don't do a ton of graphing in here, but you should be able to sketch a basic shape of the function. We talked about the mother functions a little bit already. We're going to talk about composite functions. What's a composite function? Anyone? Bueller? Matthew, or whatever he wants to be called?
Two functions, like with one other function, or one function with another function is like part of it.
Well said. Function inside a function. Polynomial inequalities. That sounds scary. It is, but you've done those already. Now we'll take a look at piecewise functions. Those are fairly common in calculus because they illustrate a lot of different things that happen. How many people think they can check off at least 3 of that list? Good. How many can check off none? You can be honest with us. We'd still love you. Okay, good. Oh yeah, step function. Yeah, I don't know if we'll talk about that. It's kind of dumb. Okay, so there's a lot of words up there. Blah, 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 blah. Some of what we're going to do, which is a lot of things that appear in blue rectangles, are going to be what I call calculus speech. They're long-winded, verbose ways of saying something that is fairly simple. Okay, you know what a function is. You know what a domain is. I'm assuming you do. The domain is all the possible x's, yes. The range is all the possible y's. But they put it in there and they use a bunch of fancy terms when they can just say domain is x's, range is y's. Down at the bottom is more important though. The difference between the independent variable and the dependent variable. So if you take a function, you choose a number to plug in for x. Because of that, the answer for y is dependent on your choice, hence the term independent and dependent. Y equals 2x plus 3, I choose whatever I want for x, I put it in there, 0 for instance. Plugging in 0 for x guarantees my answer for y, independent versus dependent variables. Since we're all fairly new to this gig, kids, if I start going too fast, just say something. If I'm going too slow, say something. No one has ever said I'm going too slow, but I thought I would make an offer there. You can either do this in your notes, or if you're feeling saucy, I made a PDF for you with these examples on that. But solve those 3 examples. I should say solve, that's the wrong word. Evaluate each of those expressions. Faith, let's do the easy one first. What's f of 3?
I got 16.
Can somebody confirm?
Yes.
Six. How? Hold on, let's back up. Notice notation here. F of x, not y equals, but f of x. We're big kids now. So, what does that mean, Faith?
You plug in 3 for x and then pick one.
Good. Okay, so let's stop for a second and go over that again, because if I keep it simple, everybody does great. And then you get to the last one and everybody loses their mind. In case you didn't hear what she just said, take that thing in parentheses, plug it into that function. Easy peasy, yes? Good. You said 16. 9 plus 7. You want to keep going?
I didn't get there yet.
Did you get a start on it?
Yeah.
Tell me.
I plugged in b minus 1 for x.
And got?
That's how far I got.
Okay.
Sorry.
I can do it. I'm pretty smart. That. Okay. The idea stays the same. Take whatever's inside parentheses, put it into the independent variable. If you're feeling all fancies in your pantsies, you could multiply this out. But not necessarily that important. I don't care. Good. Then the wheels fall off the bus. Please tell me that you've seen that before. In pre-calc, yes? Probably you just don't remember or never seen it. Okay. In calculus, that's one of the most important expressions we will see. It's called a difference quotient. And so I'll kind of help you through this, but if you keep in mind what Faith did in A and B, this becomes very easy. However, people don't want to keep it simple. They want to make it more complicated. I'm going to try to avoid that. What she told me before was take whatever's inside parentheses and put it into the function. So this f of x plus delta x means go to the function, wherever I see an x, put it in x plus delta x. X plus delta x, quantity squared plus 7. Okay, that is that. Everybody with me? Awesome. Going to change colors. Minus. Get in the habit of using some parentheses or a bracket there. This means go to the function wherever you see an x, put it in x. Well, that's ridiculous. It's just the function. And what about the denominator? The denominator is nothing. It's not f of delta x. It's just delta x. So this becomes, or it doesn't even change. It just stays delta x. If you can get to that point, you're great. However, if you're an overachiever, you could take it a little bit further and simplify it. And at some point, you're going to have to simplify. Whoops. X squared plus 2x delta x plus squared plus 7. Sidebar. Multiplying out binomials, squaring binomials, this business. We do it a lot. Whatever you need to do to multiply out that binomial, go ahead. Some people are going to want to write x plus delta x times x plus delta x and FOIL. That's okay. I use a different system. What do I use? I square the first term, I multiply 2 together, double it, square the last term. The end result is the same. Square the first term, multiply the 2 together, double it, square the last term. Okay, so that means, let's see, 7 goes away, x squared goes away. So now I've got, running out of room here, 2x plus delta x, factor out a delta x. Oh yeah, and there's my final answer. That was fairly quick, I know. But again, baby steps. If you can get to here, you're okay right now. The other stuff is algebra. But again, use the KISS method. Keep it simple, stupid. Just plug and chug. Are we okay, or am I going too fast? You're good? Okay. Because we're in the real number system, we only care about two things. Or we only have two rules. And the rules are no zero denominators. We'll ignore that discussion about 0 over 0 we had last week. And no negative square roots. Meaning, we don't have to do imaginary numbers in here. Which I don't know about you, but I'm happy about that. Not a fan. Anybody a fan? Imaginary numbers? No. No. Because of that, we are going to have to get a little restrictive. Okay. So we look at a function like this. I can't use that entire function. There are some things that are not going to fit into parts 1 and 2. What doesn't work for that function? Go.
2.
And?
0.
No, 0 is okay.
2 and negative 2.
Perfect. Okay, so now we have a domain restriction. X cannot be equal to plus or minus 2. One way to write it. Which is fine. There's another way to write it, and that would be negative infinity to negative 2 union negative 2 to 2 union 2 to infinity. I would argue that the first one's easier. Remember, with interval notation, parentheses not including, brackets including. Problems? We're good? Moving along. There it is. Domain and range. Okay, so remember, two things. No zero denominators, no negative square roots. Therefore, for this one, what do I care about? Is there a denominator? Nope. So all I have to figure out is what's going to cause problems here. Dexter, give me an example of a number that I could plug in for x that will work.
You could do 5.
5. 5 minus 1 is 4, square root of 4. Beautiful. Give me a number that doesn't work.
0.
Why?
It's going to be negative square root.
Good.
No measurement.
Okay, so taking that idea that you so expertly explained, could you please tell me what is my domain restriction for this function?
Domain has to be greater than 0. Or is it 0?
You tell me.
It needs to be-
It,
it needs to be greater than 1.
so it cannot be or is greater than 1.
It has to be greater than
What about 1?
1. I'm going to say it cannot be 1.
Cannot be 1. Agree or disagree?
Disagree.
Disagree?
Yeah.
Why?
Zero.
Okay, very good. Now, straightforward example. When it gets more complicated, how do you handle it? Solve that inequality, right? Which is exactly what Dexter just explained to us. What numbers do I have to use for x that will guarantee that the radicand, the thing underneath the radical symbol, is greater than or equal to 0? Remember, you can take the square root of 0, as you said. Solve that and we're good to go. As far as the domain, or sorry, that's the domain. As far as the range goes, I answer most range questions by looking at pictures. That's how my brain works. Okay. So whoops. I'm pretty good at graphing and visualizing what graphs look like, so I understand that that is the mother function of a square root graph shifted 1 unit to the right. And therefore, that tells me not only what the domain is, greater than or equal to 1, but it also tells me what the range is, 0 to infinity. You can play games with the range by plugging in x's and doing all that other garbage, but for the most part, I go to the range by looking at the picture. Later on, when we talk about inverse functions, there's another way to handle that, but that's in the distant future. Graphing. This is a piecewise function. Other than what I talked about a little bit with the trig functions, we don't do a ton of graphing because the assumption is that you can graph lines, you can graph parabolas, you can graph cubics. Other than that, we're about good to go. We'll talk a little bit more about semicircles and that kind of stuff. But what I would like you to do is just do that. Graph that piecewise function and see if it comes back to you. I'll help you with it after a little bit, but I'd like you to get in there and get your hands dirty first. It'll also be interesting to hear how your Algebra 2 or your pre-calc teacher taught you to graph piecewise functions. Please tell me you've seen piecewise functions before. Okay, good. Interested to see how people are taking notes, and we're covering the gamut. I have a bunch of people on iPads with white backgrounds. I have some people on iPads with black backgrounds. I have some old schoolers with their pencil and paper, which is also good. Shane, let me ask you a question. How did your pre-calc teacher teach you to graph a piecewise function? Because there's a couple different ways to do it.
Essentially, you graph the function within the parameters. So first you find all right, x is less than 0. All right, so that's your range. That's what you can work with. You can't work with anything there. And then you just graph the function.
The whole function?
No, only the function within the range.
Okay, good.
And
Stop a
then
second.
your stopping point.
Did anybody learn to do piecewise functions by graphing the whole thing and then erasing? Thank goodness. Okay, good. So then we're all on the same page. Thank you, Shane. All right, now the way I do it, and maybe your teacher taught you this, in the first problem, I'm going to figure out what the value is at 0. So I know that this part of the graph hits the point 0, 3. At that point 0, 3, is it an open circle or a solid dot? Why? Very good. Whoop. Oh boy. Or a pigtail, whatever you want to do. Okay. And as Shane said, then I know that my domain is all the numbers to the left. So I just have to graph this based on a slope of 2. Okay, so up 2 over 1, I can go get a second point here. And then I don't think I can, I'm going to have to wing it. Arrowhead's important, goes on forever. Second part. 2 endpoints, one at 0. Well, at 0, it's 0, because 0 squared is 0. And at 2, I'm up at 4. 1, 2, 3, 4. Open circle there because it's a less than. That's a little ugly there. Let me fix that. So I have my starting and ending point. Now I just kind of BS my way through it. I know it's a parabola, so it's going to look something like that. There we go. And then last but not least, this guy. Hey, what does that guy look like? What kind of straight line?
Horizontal.
Good. Horizontal straight line. Starting at 2, 1. 2, 1 with a solid dot. Whoops. Why is it doing that? That's cool. And then continuing to the right. That's good to hear, because I have had pre-calc teachers that teach the erasing method where you draw the whole line and you just erase what you don't need. I'm not a fan of it. It works. I'm just not a fan. Okay. Questions? Okay, good. In that case, I have a question for you. Why did it do that? That's my question. I'm kidding. Come on. There we go. We're back. What's wrong with that, Molly?
That dot's still there.
Correct. So it doesn't match the stuff on the right, correct? Suppose I didn't give you this. Suppose I covered up the piecewise function. You didn't know what it was. Okay, there it is, covered up. What's wrong with my picture, Mom?
There's no like the blue line. There's no intersection.
Intersection with what? The other graphs?
No like it's supposed to be like specific points.
You don't have to, as long as you get the picture. Anybody else help her out? Mason, right?
Yes.
Nice. I did that one without cheating.
It's not a function.
Bingo. Okay, it's not. How do we know if it's a function?
This is the vertical line test.
Beautiful, the vertical line test. If you can draw any vertical line through the function and hit in more than one place, it's no longer a function. So by filling in those 2 dots, I negated the fact that it's a function. As soon as it doesn't become a function, we're no longer interested in it. Or it's an indicator that you did something wrong. Okay, so be careful when you're doing, especially piecewise graphs. When you're done with them, check to make sure that you haven't violated any of those rules. If you've got a dot somewhere, above it or below it, you have to have an open circle. What if I had that? Is it still a function?
Yeah.
Sure? Good, I'm just messing with it. Yes. As long as it doesn't hit in 2 spots, it's okay. You can have big open gaps. It doesn't matter. You just can't hit in more than one spot. Beautiful. Okay, transformations of functions. I use this for my graphing. I don't know how you graph, and I don't know how you were taught to graph, but I'll tell you how I do it. Mine is all based on transformations. What I mean by that is I take a mother function, and I know what each of the other numbers does to it to get the other graph. Okay, so take a look at the third example on there. I don't know if I included it. I didn't include it. So you're actually going to have to go to that page. I should have planned ahead. Did anybody download that third example thing? No? Okay, screw up on my part. Give me a second. Okay, so my third example says the following. If we start with this graph of x squared plus 2, what does x squared plus 4 look like? We'll call that A. What does x minus 4 quantity squared look like? C is negative x squared. And D is the opposite of x plus 3. The opposite of x plus 3 quantity squared plus 1. Okay, so again, we're starting with the mother function of x squared. What does the plus 4 do to the graph of x squared? Catherine, are you raising your hand? Kind of.
Move it to the right 4 times?
No.
Or move it up?
Move it up 4 times. Good. So we'll stay with you, Catherine. What does the 4 do to it in B, as in Badger? Left or right?
Left. Right.
Which one?
Right.
You sure?
Yes.
Yes? Rest of you, left or right? Somebody's like, I don't know. I'm glad you called on her, I have no clue. Which one is it, left or right? It is to the right, correct. All right, what's the minus sign do in part C? Conrad, give it a shot.
To flip it upside down?
Are you asking me or telling me?
I'm telling
You're telling me it flips it upside down.
you. Yeah. Like normally it goes like that, but then it goes like that.
Yeah. So it goes from an up U to a down U?
Yeah.
You sure?
Yes.
Why? Present your case.
I think I remember it.
Okay, so do you agree with him, by the way?
Yeah.
And do you all just agree with him because you don't want to be called on or because you remember it also? Could you give me a convincing argument that doesn't rely on memory? Matthew?
Because all of the values you put in are like opposite of what they would normally be because of the negative sign, then all of your like ending y values are going to be negative. Or
Did that convince any of you? Convince me, yeah. Okay, so the question is then, what's the difference between this and this? Conrad, what's that do?
That keeps it up because no matter what you plug in, it's gonna be positive.
What does it do to the actual graph?
Oh. I don't know. Nothing.
Well, it does. Here's the weird thing, though. It doesn't appear to do anything to it, but it does. Alice?
Doesn't it flip it across the y-axis?
Perfect. Okay. But again, think we're doing a parabola. If I flip the parabola across the y-axis, it just reflects onto itself. Okay. Minus sign outside the function flips it over the x-axis. Minus sign inside the function flips it over the y-axis. And then you take all three of those things and you put them together, and you get D. We've covered each one of those three parts. The question about D is, which one goes first? Do you move it 3 up, move it 3 to the left, and then flip it? Do you flip it, move it, move it? Do you move it, flip it, move it? Do you move it, flip it, move it? Flip it, move it, move it? Move it, move it, move it. Okay, excellent. So what I'm hearing is I don't think it matters. I think it's flip, move, move. I think it's move, move, flip. So let's take a look at this. Okay, so let's start with the basic parabola. And you said flip, move, move.
Sure, yeah.
Okay, so flipping it over would put it down here. You want to move up 3 and over 1, or over 1 up 3?
I want to move up 3 and then to the left.
So up 3 and then over 1 would make it look something like that. Right? Okay, now what if we change the order? What if I move it first, then flip it?
Isn't it over 3 and up 1? Yeah. Just look at the parentheses.
Excellent. Good. I was seeing who's paying attention. Very good, Alice. I'm sorry, it's early in the year. I'm rusty. You're right. It would be up 3. No, it would be over 3, up 1. Yeah. Now I totally derailed the conversation. Let's summarize. The transformations follow the order of operations. Okay, let me say that again because I don't know if you've ever heard that before. The transformations follow the order of operations. Therefore, what should you do first? Please excuse my dear Aunt Sally. you would move it over 3 first. That's 1. Then you would flip, because that's multiplication. Whoops, that would be a 2. And then third is moving it up 1. Unfortunately, it does matter, because it gives you a different location of the graph every time. Wow, there's a mess. Cool. Okay, so there's a summary of everything. Again, it's in a blue rectangle, so it's a bunch of calculus speak, but it tells you what each one of those things does. All right, let's stop here for a second. Let's take like a 5-minute break. So if you need to go to the restroom, if you need to do a lap, no, I don't want to close that. If you just want to get up and stretch your legs. All right, picking up where we left off. Classification and combination of functions, also known as a, oh my God, I'm drawing my phone. Matthew, help me out. You answered the question before. Function inside a function.
Compound question?
Thank you. No, not compound function.
Composite.
Composite, thank you. You can tell I haven't done this in a while.
King of Calgary.
Okay, so again, we've got some calculus speak in a rectangle, but basically it's saying put one function inside the other function. Notice the notation. That's what's important, that little f open dot g. Don't get that confused with this. And this is a huge mistake that people run into. F of x dot g of x means f of x times g of x. F of g of x, that's a closed parenthesis, sorry there, I was excited about math, is the same thing as f composite g of x. Put g into x, sorry, put x into g, put g into f. I'll show you in the example. What's the difference between A and B? Which one goes into which? Okay, so part A would be 2 times cosine of x minus 3. Yes?
Yes.
Good. Second one, put f into g. Cosine of 2x minus 3. Be careful with parentheses. This versus, okay, that's a completely different animal. When in doubt, slap some parentheses around it. So we're going to take this to a higher level later on, and that would be not only finding out what composite functions are, but also determining the domain and range of those composite functions. And then we'll do some things later on where we'll be taking derivatives and integrals of those things. By the way, I forgot to mention, in this class we only cover 3 topics. Limits, which it takes about 2 weeks. Derivatives, which takes probably up until winter break. And then integrals, which takes us to about March. And we're done. Then we review, take tests, go away. Got that already? Good. Now, polynomial inequalities is what's going to take the most amount of time for us to review. You've done these before. You've learned different ways to do them. I'll show you how I like to do them, but they are fairly complicated. You should, at this stage, be able to solve polynomials. Solve a cubic, solve a quadratic, etc., etc. We make it more interesting by including this as an inequality. You'll recall, as I start to go through this example, what these look like, but part of the things that you do are going to be to test regions. You have to determine what works best for you. Some people are good with just plugging and chugging. That's great. There's also Boolean logic on the calculator, which I'll show you. It's a little bit more complicated, but it still works. So we'll take a nice simple example like that. It's a quadratic. Normally, if it was equal to 3x, we could solve that easily. Move the 3x to the other side, set it equal to 0, factor it, do whatever you need to do to find your two answers. By the way, basic rule of algebra, the number of solutions matches the power of the equation, right? Or the degree of the equation. This is a quadratic. You must have two answers. That doesn't really apply with inequalities, but it does when we're solving them. Okay, so make it an equation first, find critical numbers. Polynomial inequalities are not very important for us, but what they do, I just said do. What they do is set the basis for some very important stuff that we're going to do for many months. Okay, this has a direct application with stuff that we do with derivatives. Okay, those are called critical numbers because they're the numbers that make the equation equal to 0. Then you'll recall when you do this, you put those on a number line and you test regions. Please be sure that when you put them on a number line, you put them in the correct numerical order. With -2 and 5, that's not a big deal, but when you get some ugly fractions in there, make sure the smallest number is to the left and the biggest number is to the right. Is this starting to come back to you? Yes or no? Yeah, okay, good. This is an example where you don't have to use Boolean logic, but I will show you how to do it in a second. The way Boolean logic does is the thing it does is it uses your calculator to test regions for you. So get out your calculators, please. Boolean logic does a very simple thing. It allows you to type in an equation or an inequality and it will simply tell you yes or no. That's it. What you have to decide is it worth the hassle to go through the calculator to do all this work, or can you just plug and chug? For instance, if I'm solving this problem and I don't know this yet, what would be a good number to choose there? 0 would be outstanding. If I plug 0 in there, is -10 bigger than 0? No, that's false. Therefore, it doesn't work. That didn't require a calculator. But as the problems get more complicated, you might want to try doing this on the calculator. So the first thing you have to do is store a number. So hit 0, store x. You can get to the x either using the x button, or there is that button up on top that says xt, theta, and n. Store is on the left, it says sto on it. If I lose you along the way, please holler. So your calculator should display when you hit 0, sto, x, it should display 0.
Yeah, the math I should.
How are we doing so far? Good? Now, whenever you type x into the calculator from this point on, it's going to plug in 0. Then, you have to type this into the, into the home screen, just as it appears. So you're asking yourself, self, where's that greater than? Hit the math button. Go over to, I'm sorry, I lied. It's above math, the test button. So second math. Yeah. So on the home screen, you're going to type x squared minus 10. Second math greater than 3x and hit enter. What does it tell you? 0. Now, this is the thing you need to remember about Boolean logic. 0 is not the answer. 0 means false. 1 means true. Okay, so let's do it again. Take a number over here, let's say 7. Store 7 into x. stow, or 7 stow x enter. You could retype in the inequality or just scroll up to it and hit enter, and it should give you a 1. Way back when, at the very beginning, you'll remember I said I'm going to give you a bunch of tools. That doesn't mean you need to use it. You may find this way too complicated. That's okay. But at least I've shown it to you. You have an option to use it later on when the problems get very ugly. Okay? 3 steps to these. Questions before I move on? Okay, so I'm going to solve that one. This ramps up pretty quick. Now, before I get started on this, what can you tell me about x? Go.
Can't be 5.
Or
The other one.
the other one.
Negative 3 over 2.
You're right. Okay. Again, real number system. No 0 denominators, no square root, negative square roots. We don't have any square roots, so we're good. So over here on the side, I'm going to say x cannot be equal to 5 and negative 2/3. Oh, I lied. 3/2. Jeez, this guy. You might want to switch to a different calc teacher. I don't know what I'm doing. That's just going to sit there and bother us for a while. Now we're going to solve this. Step 1, turn it into an equation. Well, okay, I'm going to cheat. I'm too lazy to rewrite. There you go. Equation. How do I solve that equation? Please.
You multiply x minus 5 to both the denominator and numerator on the other side to have the same.
Perfect. What's the fancy mathematical term for that?
Putting them in the same terms. Cross multiply.
I've already demonstrated that my math skills are rusty, so keep an eye on me. Agree or disagree? Agree? We're good? Okay. In this problem, I had 2 critical numbers. In this problem, it appears I have 1 critical number. I actually have 3. So I have 3 numbers to put on a number line in the correct numerical order. Now, the problem with 3 critical numbers is all of a sudden I have 4 regions to test. The most common mistake when solving these types of problems is making the assumption that if the first one turns out true, then it's going to go true, false. Or if the first one is false, it's going to go false, true.
Why do you have to put in things that can't happen?
Because it determines right away that x can never be those values. So if I didn't include these 2 numbers, then we would plug in a number over here like 0 and it would speak for the whole area. But in that whole area, there's 2 numbers that don't work. So it generates new areas. Over here, what number do you want to add or use, Emma? -9. So if I plug -9 in here, I get 2 over -15 is less than or equal to 2 over -14. Holy smokes. I don't know. Which one's bigger? Is that a true statement? Because as the denominator of a fraction gets smaller, the denominator, or the value gets bigger, and as the denominator gets bigger, the value gets smaller. So, true. Boink. Good number in here? I mean, there is no good number. Just pick one. -5. Great. I will say this. What's a good number in here? 0. Okay, so let's skip this one because I'm too lazy to do it. If I plug 0 in there, I get 2/3. Is 2/3 greater than or equal to 2 over negative 5? No, that would be false. And then over far to the right, take a big honking number and plug it. So you go through and do that. Now, you might realize that this 2 over negative 15 less than or equal to 2 over negative 14 doesn't work, and you can pick up the calculator and do the Boolean logic. Store, I forgot what you said, negative 9?
Yeah.
Store negative 9 in there for x, type in this original inequality, and see if it spits out a 0 for false or a 1 for true. You have a couple different options. Okay? Questions? We're done.